So instead of looking for the exact area of the region we're interested in, let's start by just estimating. See if we can come up with some estimates for the area of this region here, this curved region between 0 and 3. What are some estimates? Well, there's a few things we could probably do immediately just to get some estimates. One thing I can do, you don't need to bother writing this down in your notes. I'll let you know when we can start, but this is just sort of getting some ideas. We could connect those two endpoints with a straight line. Now we've got a triangle. And we could say, okay, I know the area of that triangle, and so the area of the portion under the curve would be smaller than the area of that triangle, and so I can get an upper bound on the area of the portion under the curve. That's possible. We can do that. That'll give us an estimate, an upper bound for the area. What else could we do? Well, maybe we should actually just work that value out just for fun. So that would be 3, 9. And so the height there would be 9. The base would be 3. So this would be 1/2 3 times 9, or 1/2 of 27, which is 13.5. So the area is smaller than 13.5. The area of the curved, under the curved portion, under the curved region, is about 13.5. What else could we do? Well, we could maybe do something like this. We'd say, well, now I want a lower bound maybe. Okay, pick any point on the curve, draw the tangent line there, and now we've got a straight edge to work with. There's another triangle, and so the area of this triangle, we can work out what it is, and we'll get a lower bound for the area of the region because I'm missing some portions. There's some portions that are in the region that I don't count by looking at the area of the triangle. So I can get a lower bound. But I've got lots of choices for this point that I could draw the tangent line at. So I could probably come up with, draw the tangent line at a point A, work out the equation of the tangent line here, work out that intercept, and then get a function for this, the area of the triangle, as a function of A, and then look for the maximum as A ranges from 0 to 3. So now we're into calculus 1. We could do this. I'll just show you what this would look like dynamically. So here's our point that I've constructed the tangent line at, and then I can work out the area of that triangle, and here I've got it worked out at 7.82, and I can move that point, and I get all these different triangles and all these different areas. And if we watch the numbers, so I'm starting at a low number, it's increasing, it gets up to 8, and then it starts dropping off again. So somewhere around 2, the area of that triangle becomes maximum, has a maximum value of 8. So that gives me a lower bound for the area under the curve. Got to be bigger than 8. And I know it's lower than 13.5 by that other argument. So I know it's somewhere between 13.5 and 8. So these are just sort of estimates that we can get using ideas from calculus 1. What we're going to do now, and this is where you can now start jotting things down in your notes, what we're going to do now is try to work out an estimate for this area using just rectangles. That's what we're forming the basis of this idea of area from. Area of a rectangle we know, area of other regions, we're going to use the rectangle to get areas of other regions to make sense of what that means. So what I'm going to do is, well, I could use a big rectangle right around it, a rectangle of height 9, and if I use a rectangle of height 9, the base would be 3. I'd get 3 times 9 or 27. That would be a rectangle that's bigger than the region that I'm interested in, so I know 27 is an upper bound. Seems to be a rather large upper bound. Maybe I can be a little bit better. So what I'm going to do is I'm going to slice the region up into 3 pieces. So we're going to split the interval into 3 pieces. So 0 to 1, 1 to 2, and 2 to 3. And now what can we do with these 3 pieces? Well, one thing I can do is use rectangles to approximate each of those pieces. So now we're going to use the right-hand endpoints of the intervals to form these rectangles. Right, there's some choice here for, let's say, look at the interval from 1 to 2. I've got a choice of how I can use a rectangle to approximate. I can use the right-hand endpoint and cap it off above. I could use the left-hand endpoint, cap it off below. Or I could really use any rectangle that sort of is any height between that sort of lower bound and that upper bound to get an estimate for the area of that region using a rectangle. I'm just going to use the right-hand endpoints as I've drawn here. So I'll sketch this in green because we're going to do some other ones as well, so I just want to color code them. So the area, the actual area under the curve, the area under the curved portion of the curve, can be approximated by the sum of the areas of these three rectangles. I'm going to call that R sub 3. The R stands for the fact that I've used the right-hand endpoint for the interval, and the 3 stands for the fact that I've used three slices, or 3 intervals, or 3 rectangles, however you want to look at it. So what's R3? That would just be the sum of the areas of those 3 rectangles. Each of the rectangles has base 1. The height of the first rectangle, well, we're using the right-hand endpoint, so that would be the function value at 1. The function is the squaring function, so this would be 1 squared. Plus 1 times, the next rectangle has height 2 squared. And the next rectangle has height 3 squared, or 9. And so there's the area of those 3 rectangles. We can work that out. That's 1 plus 4 plus 9, so that's 14. And so we know that the actual area under the curve, which I've denoted by A here, is smaller than 14. Here's the fun part. We can actually use the left-hand endpoints to do this as well. So now use left-hand endpoints. Of the intervals. And let's see what that gives us. I'll use red to denote this. So the left-hand endpoint, that first interval, its height of 0. So there's no rectangle here. I'm just going to draw a horizontal line. There's no rectangle there. But if I use the height of the left endpoint for the second one, there's a rectangle that we have. And then for the third one, there's our other rectangle. So the actual area under the curve, we could approximate it by L sub 3L, meaning that we're now using the left-hand endpoints of each interval as the place where we cap off that rectangle for the height. So this is going to be 1, 0 squared, plus 1 times 1 squared being the height of the second rectangle. The third rectangle has height 2 squared. So that's base, which is 1, times 2 squared. That's 0 plus 1 plus 4, which is 5. So what do we have? We have that the actual area under the curve is trapped between 5 and 14. So there's our estimate. We know that the actual area under the curve is between 5 and 14. Now, you may think, well, that's such a big region, we really haven't done a very good job of estimating. And yeah, that's true. We haven't done a good job of estimating at this point. But the point here is that our technique, we can generalize this. And it's very straightforward to do that. There was nothing special about me taking 3 rectangles. I took 3 just because it made the slices happen on these integer values on the x-axis. But other than that, there's nothing special about 3. So what can we do? Well, let's have a look at a visualization. So there's our region. We've got the right-hand rectangles, the rectangles that were constructed using the right-hand endpoints. We've got 3 of them. And there's our value, what we're going to call the Riemann sum, the sum of those rectangles, the area of the rectangles. That was 14. So we worked out that already. Now here's the thing. We can just bump up the number of rectangles, do the same calculation. There's nothing difficult about that calculation. It was just all the areas of the little rectangles were just their base times the corresponding heights. So we can work those values out. So I could do it for 4 rectangles, or 5, or 6. And what you notice about the Riemann sum is those numbers are dropping. Each one of those numbers is an upper bound on the actual area we're looking for. So I know at this point, once I've used 10 rectangles, that my actual area is less than 10.395. Oh, but if I use a rectangle, it's less than 10.264. 12 rectangles, 13, 14. Notice that the more rectangles I take, the better those rectangles seem to be at approximating the actual area under the curve. I'm all the way up now to 70 rectangles, and I've got that the sum is roughly 9.19. So that means that my actual area is less than 9.19378. And I can go up to 80 and drop that number down even more. I've got 80 rectangles. I know now that I've got a pretty good estimate for the area under the curve. Just looking visually at it, I can see that I'm overestimate because there's these little bumps that are coming up from the sides of the rectangles. But I've got a pretty good estimate. Now we can do the same thing with the left-hand endpoints. Remember, in this particular case, those left-hand endpoints, they formed a lower bound. Those left rectangles were always of area smaller than the actual slice I'm looking for. So there's our Riemann sum of 5. And now I want to crank that number up. The Riemann sum is getting bigger and bigger in value. I'm up to 34 rectangles. If I keep going, and head all the way up to 80 rectangles like we were before, I know that 8.83 is a pretty good estimate. So my right rectangles were about 9.2. My left rectangles were about 8.8. So I know that the actual area is between 9.2 and 8.8. This is what I mean by we can now sort of ramp this up and generalize for more rectangles. And so I've got a pretty good estimate. And we're going to see now that we can actually do this in a limit. In a limit. So rather than just taking a distinct number of rectangles, 80 in this case, I want to say, what happens if I let the number of rectangles go to infinity? If I let the number of rectangles go to infinity, then that should give me rectangles that exactly match the area under the curve. That's what we're going to define the area under the curve to be. The limit of this process of using rectangles to approximate. So let's see the details of this. So to get us thinking in this direction, I want to start by using 4 rectangles, and we'll see what the details of the calculations are with 4 rectangles. But really, we're coming up with this question: can we do better? Can we do better? We found that the area is between 5 and 14. Can we do better? And we saw that, yes, we can do better. How? Use more rectangles. Use more rectangles, maybe, exclamation point. Use more rectangles. Make them thinner. Use more of them to approximate the area under the curve. And if you do that, then you'll get a better approximation. So can we do better? Yes, use more rectangles. So let's use 4 rectangles now. Now I'm just doing the 4 rectangle case, so we get a feeling for what the calculations actually are. Then we're going to go and do the general n rectangle case, where n is any number. Could be 3, could be 4, could be 80. So in 4 rectangles, what do the calculations look like? So here's our region, up to 3. And when we split it up into 4 rectangles, so we've got 1 rectangle, 2 rectangles, 3 rectangles, and there's the 4th one. What are these values here? Well, we're going to assume we're splitting it into 4 equal width rectangles. So what are the widths of each of these rectangles? Well, we're taking an interval of length 3, and we're splitting it up into 4 equal parts. So each width would be 3/4. So 3/4 plus another 3/4 is 3/2. We're smack dab in the middle of that interval, plus another 3/4 is 9/4, plus another 3/4 gets us out to 3. So split region, or maybe I should say split interval 0 to 3 into 4 what we'll call sub-intervals. 4 sub-intervals. 4 intervals that are each a subset of the original interval. And what are our 4 sub-intervals? Be 0 to 3/4, 3/4 to 3/2, 3/2 to 9/4, and 9/4 to 3. Now what do we do with this? Well, we do just what we did above. We look at the right-hand endpoints, construct those 4 rectangles, compute the area of all 4 of them, and add them all up. So for the right endpoints, of each of those intervals, we have that the actual area under the curve, which I'm denoting by A, is approximately the area of these 4 rectangles, so which we'll call R sub 4. R, again, for right-hand endpoint we're using, and 4 because we're using 4 rectangles. And now what is it? Well, it's the width of the rectangle times its height. What's its height? That would be 3/4 squared. This is a squaring function. So if I know the x value, I square it to get the y value. Plus the width of the second one times 3/2 squared. It's going to be more convenient instead to write 3/2 as twice of 3/4. In other words, it took me 2 jumps, 2 of these 3/4 jumps to get to 3/2. So I'm going to write it as 2 times 3/4. A part of dealing with these expressions is to get them in a form that are easier to work with, and it's going to be easier to work with 3/4 rather than the 3/2. Plus 3/4 times, now that 9/4 is actually 3 of those 3/4. It took us 3 jumps to get to that value there. So that would be 3 of 3/4 all squared. And then plus the last rectangle, which was 3. The height would have been 3 squared, but I'm going to write it as 4 times 3/4 all squared. Again, because that 3 is really obtained by starting at 0 and making these 4 of these 3/4 jumps. Now at this point, we just have to add up all these values and we get R4. But I've written them in this way so we can see that this addition sort of simplifies down to give us a nice pattern. What's the pattern? Well, there's a 3/4 and a 3/4 squared, so there's a 3/4 cubed in the first one. And that's actually something that appears in all of them. 3/4 and a 3/4 squared. That's another 3/4 cubed, and another 3/4 cubed, and another 3/4 cubed. So all of those 3/4 cubes can come out. And what is left is 1 from the first one, plus when I factor out the 3/4 cubed, I'm left with just a 2 squared in the second one. So I'm going to write a little 1 squared there just so we can see a pattern happening. Plus, I've taken out all the 3/4. That leaves me with just a 3 squared. Plus, and the last one is a 4 squared. And so this adds up to now 3/4 cubed times, and the sum of these numbers is 16 plus 9 plus 5, so that's 30. So there's our sum of our rectangle, area of the rectangles using the right-hand endpoints, what we call the right-hand Riemann sum for 4 rectangles. So our area, we know, is smaller than this. Now we can use left endpoints as well. So again, we're going through this process just so we can see how these calculations sort of come out. So if I'm using the left-hand endpoints, using that value, that value, that value, and that value. So these are the rectangles. What do we have then? Well, the area under the curve is approximately L4. What is L for? Some of the areas of these 4 rectangles. Each one of them has a base of 3/4, and then to get the heights, well, you notice that the heights, we're really just using the left-hand endpoint. So instead of starting with the height happening at 3/4, I'm starting with the height happening at 0 for the first rectangle, and then I'm just using the heights that I used before, with the exception that I'm not using the height at 3 because I'm using the one before it. So we get the exact same calculation as we did before, except instead of using 1 squared, 2 squared, 3 squared, and 4 squared, which were really corresponding to these points here, 1 squared, 2 squared, 3 squared, and 4 squared, because that's how many jumps it took me of these 3/4 to land on those points. I'm instead using this one, and this one, and this one, and this one. So I'm really just using 0 squared, plus 1 squared, plus 2 squared, plus 3 squared. This is part of the convenience of using, in your calculations, recognizing patterns and using appropriate representations of the points, is that maybe you can extract some things that you might otherwise not have seen just going and doing the brute force calculation. So in this case, there should be a cubed here, of course. We get a value of 3/4 cubed, and that's 9 plus 5, or 14. And so there's the value using 4 rectangles, and therefore our actual area is trapped between 3/4 cubed times 30 and 3/4 cubed times 14. We can work out the values of these things. This is roughly 12.625. This is roughly 5.90625. So we have that our actual area is somewhere between 5.9 and 12.6. So that's using 4 rectangles. We can use 5 and 6, and as we saw in visualization, we can go all the way up to 80 and then beyond. It's just a simple matter of, we wouldn't do that by hand. We'd have a computer calculate those values, but it's nothing more than doing some multiplications and some additions, something that a computer is very happy to do and doesn't take more than a few lines to program. What we can do now, though, is generalize this. Generalize this. So in general, let's see what happens. In general, use n rectangles, where n can be any number, and let's see what these calculations give up. So we're actually going to do the same calculation we just did, but instead of using numbers, we're going to use expressions involving n. So here's our interval. We're going to call that x sub 0, which is just a, x sub n, which is just b. We're going to split it up into n rectangles. So here's our rectangles, and that sort of pattern continues. There's another rectangle all the way up to here. There's our last rectangle. So this would be x sub 1, x sub 2, x sub 3, and we just continue, maybe x sub I minus 1, x sub I, and then all the way up to, and then there would be an xn minus 1, all the way up to xn. So there's our our slices, and we're going to use rectangles to approximate the area of the slices. So we're going to split the interval into n subintervals, which we started at x0 to x1, x1 to x2. Those are just the names we're giving to the endpoints, all the way up to xn minus 1 to xn. And here, that was A, and the last one was B. What do we do after we split? We start computing areas. So we can use right-hand endpoints. And you'll see that even though it looks like it's probably going to be more difficult because we're using more rectangles, we're using n in general than using 4 or 3 in the past, turns out that when we work at this more general case, we don't get bogged down into all this finicky arithmetic with the actual numbers, because we're using now these expressions in n. And if we do this right, it's going to be a lot more clear as to how these calculations work. So what do we need for these endpoints, or for the rectangle sum? We need to know the width of each of the rectangles. So what's the width of a rectangle going to be? Well, we took an interval of length. In this case, A was 0 and B was 3, so maybe I should have written that here instead. A, which is 0, and B, which was 3. We took this interval of length 3, and we split it up into n subintervals. We slice it up into n equal sized pieces. So the width of each piece is going to be 3 over n. We're going to call that delta x. Now, what are our expressions for each of these xi's in terms of n? Well, let's just think about what happens. As I start with x0, which is 0, what's x1 going to be? Well, I'm just moving over the width of the rectangle, or the width of the slice. And that's delta x, which we just happen to know is 3 over n. So that would be 3 over n. What's x2? Well, I would have had to have moved over 2 slices, each of width delta x, so this would have been 2 delta x. What's x3? That's 3 delta x. All the way down to xn, which would have been n delta x. So I had to move over n slices to get to that. And of course, just a quick check, n times delta x was 3 over n, so that's 3, and yes, xn is 3. So this is now an expression for all of these intermediate endpoints. And that's going to make our calculations really simple. So what happens with the right-hand endpoints? Again, I'll color code like we did before. The actual area under the curve is approximately the area using n rectangles, where I've used the right-hand endpoint as the height. What is the sum of the areas of these rectangles? Well, the first rectangle, it has base delta x. What's its height? Its height is going to be the value of x1 squared. What about the next rectangle? Well, its base is delta x. Its height would be x2 squared. All the way up to delta x, xn squared. What is x1? Well, we found that to be delta x. x2 was 2 delta x, so a lot of this stuff simplifies down. That's a delta x squared. That's a delta x times a 2 delta x squared, plus all the way up to delta x times n delta x squared. I've got all these delta x's. In each term, there's one of them being squared and another one by itself, so each term contains a delta x cubed in it. And when I factor those out, I'm left with a 1 plus a 2 squared plus a 3 squared plus all the way up to n squared. And I'm going to throw a square on the 1 because it doesn't change the value. It's still 1 squared, and now I see a pattern. This was the same pattern we observed above. If we look above, we see that when we used 4 rectangles, we had to sum 1 squared up to 4 squared, and we used 3 divided by 4 all cubed. Now we see, in general, that it's 1 squared up to n squared, and what was delta x? It was 3 divided by n all cubed. Same pattern we had before. What about our left-hand endpoints? If I use the left endpoints, you could work through the details just like we did for the right-hand endpoints, but you will observe that the same pattern has to occur, except everything's just been shifted. Everything has just been shifted to the left. I'm using all the left-hand endpoints now, so I'm using x sub 0, but I'm not going to use x sub n in my calculations. So this would be delta x all cubed. 0 squared plus 2 squared plus 3 squared plus all the way up to n minus 1 all squared. And so what we have is a way to estimate the area under the curve and really refine our estimate to be as good as we want by just taking n large enough. So therefore we have that a is trapped between Rn and Ln for all n. 1, 2, 3, 4, all the way up. And so I want to know a good estimate for A. Maybe I'll take n to be 80, or maybe n to be 100, or n to be 1,000. And taking n to be any of those values, I just have to add up essentially 1 to 1,000 squared, or 0 to 999 squared, and multiply by the delta x, the 3 over the corresponding n value, 3 divided by 1,000. And I can get a good estimate for what the area under the curve is. All right, so there's our process for estimating. And we're using what are known as these right-hand or left-hand sums, which are called Riemann sums. And so that's essentially our process. That's how we're going to look at solving the area problem. And it will turn out that not only are we getting estimates here, we can actually get exactness. How do we get exactness? Let's have a look.